The analysis of convergent-divergent nozzles is common in many industries. In this video, I'll show you how to model a CD nozzle and investigate the normal shock within it. Hello, I'm Armin. Before we begin, let's talk briefly about the topic. Convergent-divergent nozzles are inherently 3D, but for simulation purposes, we can simplify them as a quasi-1D flow. In fluid dynamics, 1D flow assumes velocity, pressure, temperature, and density vary only along the streamwise direction with uniform cross-sectional properties, making it valid for constant area ducts. Quasi-1D flow extends this by allowing variable cross-sectional area A of x as in convergent-divergent nozzles. Here, flow remains 1D in the axial sense, but area variation modifies the conservation equations, enabling analysis of compressible effects such as choking, shocks, and nozzle performance. A convergent-divergent nozzle, CD nozzle, is widely used in the aviation industry and in turbines. The nozzle has a convergent inlet and a divergent outlet. If the inlet flow velocity is subsonic, the flow accelerates to sonic speed at the throat and then becomes supersonic in the divergent section. On the other hand, if the inlet flow is supersonic, it decelerates and becomes subsonic in the divergent part of the nozzle. A normal shock occurs in a CD nozzle when the exit pressure is high enough to prevent supersonic flow throughout the divergent section. The shock forms perpendicular to the flow somewhere in the divergent region, causing the supersonic flow to suddenly decelerate to subsonic speeds. This abrupt transition results in a sharp increase in pressure, density, and temperature. After the shock, the flow continues subsonically toward the nozzle exit. In ANSYS Fluent, we will use a 2D axisymmetric model to simulate a quasi-1D flow in the nozzle. The working fluid is compressible air, modeled as an ideal gas with the Sutherland viscosity model, since viscosity varies with temperature. At the inlet and outlet, we will apply pressure boundary conditions and vary their values to examine the effect on the normal shock location. To obtain accurate initial values, we'll use full multigrid initialization, and for better convergence, we'll apply the pseudo-time method. After solving the model, we will analyze velocity and pressure contours under different inlet and outlet pressure conditions. That's all you need to know. Let's start modeling. The model is axisymmetric, so we can simplify it to 2 dimensions. Since this is a CFD model, I'll double-click on fluid flow. I'll click on the Geometry cell to open the Properties window and change the analysis type to 2D, since axisymmetric problems are modeled in 2 dimensions. Next, I'll create the geometry. Right-click on Geometry and select New SpaceClaim Geometry, because we want to build the model in SpaceClaim. We need to define the profile of the convergent-divergent nozzle. First, I'll change the sketch plane to XY. I'll click on New Sketch Plane, select the XY plane, and switch to Plan View for a perpendicular view. Let's begin sketching. I'll select the Line tool from the Sketch tab, click on the origin, and draw a 100 mm line along the x-axis. After pressing Escape, I'll click on the origin again and draw another 100 mm line. Now let's create the nozzle inlet. The inlet diameter is 60 mm, but since we're only modeling half of the geometry, I'll enter 30 mm. Next, I'll define the walls. The slope is 78 degrees with a length of 90 mm. You can switch between defining the angle and the length by pressing the Tab key. I'll draw the outlet the same way as the inlet, with a diameter of 30 mm. After that, I'll set the wall slope to 78 degrees and the length to 90 mm. The geometry looks consistent so far. Finally, I'll connect the 2 endpoints with an arc to form the nozzle throat. I'll select Rounded Corner from the Sketch tab, click on the 2 endpoints, and generate the arc, The nozzle profile is now complete. I'll click on End Sketch Editing. As you can see, the nozzle profile is now complete. This profile will revolve around the axis to form the full geometry. The next step is to define the boundary conditions: inlet, outlet, axis, and walls. I'll start by selecting the inlet, click on Create Name Selection, and type Inlet. Next, I'll select the outlet, click on Create Name Selection, and type Outlet. For the axis line, I'll select it, create a new name selection, and type Axis. Finally, I'll hold Control, select the upper surface, click on Create Name Selection, and type Walls. Everything looks correct. We don't need any further edits in SpaceClaim, so I'll close it. In the second step, we need to generate the mesh for our model. I'll double-click on Mesh to open it. Before adjusting the settings, it's useful to check the default mesh. I'll right-click on Mesh and select Generate Mesh. As you can see, the default mesh is too coarse, so we'll refine it by adding a sizing control. I'll right-click on Mesh, go to the Insert menu, and select Sizing. From the options, I'll choose Face Selection, click on the face of the geometry, and hit Apply. Now, I'll right-click on Mesh and select Update from the menu. I forgot to set the element size, so I'll adjust it in the Details window. Let's try 3 mm as a starting point. After updating the mesh, it looks acceptable, but reducing it further to 2 mm gives a better result. Since this is a nozzle, I also want to create a structured mesh. To do this, I'll right-click on Mesh, go to the Insert menu, and select Face Meshing. Then I'll select the geometry and click Apply. Now let's update the mesh again. Here you are. We now have a fine, structured mesh. Before moving on, let's quickly recheck the boundary conditions in the name selections: Inlet, Outlet, Axis, and Walls. Everything looks correct, so we can close the mesh window. If you see a lightning icon instead of a check mark, it means the mesh needs updating. Now let's move on to the setup. I'll double-click on Setup. In the Fluent Launcher window, make sure to check Double Precision to improve accuracy. Also, specify the number of CPU cores for the simulation. I'll type 8, but this depends on your computer. Finally, click Start to proceed. We're now in the Setup environment. In the Task Page section, we need to adjust a few settings. Since our model is axisymmetric, I'll enable the axisymmetric option. Because the fluid is highly compressible, I'll change the solver to density-based. If compressibility were low, we could use pressure-based, but for this nozzle problem, density-based is required. Next, let's set up the material. Expand the Material section, and under the Fluid subsection, double-click on Air. Air is the default fluid, and you can define or select another material if needed. In the Properties, change Density from Constant to Ideal Gas to account for compressibility. Also, since temperature changes during expansion and contraction, change Viscosity from Constant to Sutherland. The Sutherland viscosity model is widely used for compressible flow simulations. Click OK to close the window, then click Change Create to update the current material and close the Materials window. Finally, let's check the viscous model. Expand the Model section and double-click on Viscous. If you want to perform an isentropic simulation, you can select Inviscid. But since I'm running a realistic simulation, the K-omega SST model is the most suitable choice. I'll leave it as is and close the window. Next, we need to specify the boundary conditions for the inlet and outlet. To do this, I'll expand the Boundary Conditions section. You'll notice the axis is already defined automatically because we named it earlier in SpaceClaim. Expand the Inlet section. By default, the boundary condition is set to Velocity Inlet, but I want to change it to Pressure Inlet. Right-click on it, go to Type, and select Pressure Inlet. In the Momentum tab, we need to specify the gauge total pressure and supersonic initial pressure. However, before entering these values, it's better to set the operating pressure to 0. By doing this, the gauge total pressure directly becomes the total pressure. This approach also improves convergence because pressure variations are much smaller than atmospheric pressure. To adjust this, I'll close the inlet window, go back to Boundary Conditions, and double-click on it. In the task page, I'll click on Operating Conditions, set the operating pressure to 0, and hit OK. Now let's return to the inlet. Since the gauge total pressure is now interpreted as total pressure, we can directly enter the stagnation or total pressure value for the inlet. Let's specify the inlet conditions. For the total pressure, or stagnation pressure, I'll set the value to 200,000 Pascal. For the supersonic initial pressure, it must be smaller than the stagnation pressure, since it typically represents the static initial pressure. I'll use the atmospheric pressure value. Next, go to the Thermal tab. Here, we can specify the inlet temperature. I'll keep the default setting. Click Apply, and then close the window. Now, let's move to the outlet. Expand the Outlet section. As you can see, Pressure Outlet is already selected by default. Double-click to open it. In the Gauge Pressure field, we need to define the back pressure. Under Design Conditions, the back pressure is equal to the ambient or environmental pressure, so I'll enter 1 atmosphere. I won't make any further changes here. The backflow total temperature can also remain at its default value. Click Apply and close the window. With the boundary conditions set, let's move on to the methods. Double-click to open it. Here, we can adjust the numerical schemes. It's recommended to enable higher-order term relaxation, which helps stabilize the solution. Also, under Options, change Flow Variables Only to All Variables for better convergence. Click OK. The next step is Initialization. Every simulation requires initial values. Hybrid initialization is selected by default, and it usually works better than standard initialization. I'll keep the default settings and click Initialize. The residuals look acceptable, but for improved convergence, we can use FMG initialization as well. Before we start solving, let's talk about FMG initialization. FMG stands for Full Multigrid Initialization. It provides a better initial approximation of the flow field compared to the default hybrid initialization, which helps the solver converge faster and more reliably. To see its effect, let's first generate a pressure contour. Expand Graphics, right-click on Contours, and select New. Rename the contour to Pressure and click Save. As you can see, with hybrid initialization, the pressure distribution in the nozzle is nearly uniform at about 1.01 times 10 to the 5 pascals. Now let's apply FMG initialization. Open the FMG panel and click Calculate. Then return to the pressure contour and click Display. Notice the difference. FMG provides a more realistic pressure distribution even before solving, which improves convergence. Next, let's run the simulation. Go to Run Calculation, set the number of iterations to 1000, and click Calculate. The solution is complete. I'll click OK and check the residuals. As you can see, the solution did not converge. To better understand the flow behavior, let's inspect the velocity field. Right-click on Contours, select New, change the variable to Velocity, and name the contour Velocity. Click Save Display and close the window. As you can see, a normal shock appears in the nozzle, which confirms that the physics look reasonable. However, the solver still hasn't converged. To improve stability, let's adjust the under-relaxation factors. Navigate to the Controls section and set the Courant number to 1. This makes the solution process more stable. Now, return to Initialization, re-initialize the model, enable FMG initialization, and run the calculation again. Checking the residuals, it seems the solution is progressing more smoothly this time. I continued the simulation up to 7,000 iterations, but the model still did not fully converge. Before modifying the solver strategy, let's check the accuracy of the results using a mass balance. Go to the Results tab, select Fluxes, choose the inlet and outlet boundaries, and click Compute. As you can see, the net result is not close to 0, which indicates that the solution has not converged. For a converged solution, the net mass balance should be nearly 0. I'll close the window. Go to Methods and change the pseudo time method to Global Time Step. Once this solver setting is updated, notice that the Courant number control disappears in the Controls section because it is no longer required. Now let's solve the model again. Go to Initialization, re-initialize the model, and enable FMG initialization. Open Run Calculation and click Calculate. The solution is complete. Click OK and check the residuals. This time, the solution is fully converged. To confirm, let's recheck the mass balance. Go to the Results tab, select Fluxes, and click Compute. The net result is now approximately 0, which confirms that the solution has converged. I'll close the Fluxes window. Sometimes it may be necessary to use stricter convergence criteria. To do this, navigate to the Monitors section, expand it, and open Residuals. Here you can decrease the absolute criteria to more stringent values. For example, I'll add 10 to all the absolute criteria. Click OK and run the calculation again without reinitializing. The solution is complete, and now it satisfies the tighter convergence criteria as well. As you can see, the solution is fully converged and the net flux has decreased further. I'll close the Fluxes window. Looking at the velocity contour, we can clearly see the presence of a normal shock as well as boundary layer separation. To get a better understanding, let's switch from velocity magnitude in meters per second to Mach number. I'll open the velocity contour, change the variable from velocity magnitude to Mach number, and click Save Display. As you can see, the maximum Mach number is about 2.24, and choking occurs at the throat of the nozzle where the Mach number reaches 1. Now let's explore how inlet pressure affects the shock location. What happens if we decrease the inlet pressure? Let's try it and see. I'll go back to the inlet boundary condition and under the Momentum tab, change the total pressure to 150,000 pascals. Click Apply and go to Initialization. I will reinitialize the solution and enable FMG initialization. Finally, I'll run a calculation. The solution is complete. Now the shock occurs much closer to the throat because the inlet pressure has been reduced. If we decrease the outlet pressure or increase the inlet pressure, the shock wave moves downstream toward the outlet. This clearly shows the strong dependence of shock position on both inlet and outlet total pressure. Let's test this by lowering the back pressure. I'll double-click on the outlet boundary, set the pressure to 40,000 pascals, and then go back to initialization. I'll reinitialize the model, enable FMG initialization, and run the calculation. The solution is complete. Now we can see that the shock wave has moved farther downstream, indicating that the flow has adjusted to the lower back pressure. That concludes this tutorial. Thank you for watching. If you found this helpful, please like the video and subscribe to my channel for more tutorials.